Hello and welcome to the lecture series on applied thermodynamics. In today's lecture we're going to take up a new chapter, that is vapor powered cycles. And in today's lecture we're going to look at a schematic view of a typical steam power plant, and we are going to look at various subsystems present in the steam power plant, followed by we're going to look at a comparison between Rankine and Carnot cycle, typically looking for the best representative cycle for the operation of steam power plant. And at the end we are going to look at performance parameters related to a steam power plant. Now let us look at the schematic view of steam power plant. Here we have a schematic view of a steam power plant, which is also called as thermal power plant. The power plant makes use of water as a working fluid, and which will be converted to steam in the boiler, which is shown here. And we see that we have a various components here, and we have some subsystems like A, B, C and D. Among this, subsystem A represents chimney and the furnace, subsystem B represents turbine, condenser, feed pump and boiler, and subsystem C represents cooling tower and the water treatment, and subsystem D represents power production point, where we have a generator and the grid. Let us now move forward, and we are going to focus on the following components, basically, which belongs to subsystem B. Our focus will be on boiler, turbine, condenser and feed pump. So this is where we see the heat is added into the system at the boiler through the furnace, and work is produced in the turbine, and at the same time we also see that there is a heat that is rejected at the condenser, and we have a feed water pump here to pump the water back to the boiler to keep the cycle moving. Now let us look at the components of a power plant, focusing on the four components which I have shown just now. So here we have turbine, and the purpose of the turbine is to produce the shaft work, and the shaft is further connected to a generator, and the generator is further connected to a grid system. And we see that at turbine the steam is going to expand from process 1 to 2, thereby the pressure is lowered, at the same time the temperature also is lowered. Further we see that from process 2 to 3 the expanded fluid, that is steam, is going to get condensed in the condenser. A condenser is basically a kind of heat exchanger, where we have some cold water circulated around the condenser, thereby heat is extracted. We can see here Q out, heat is extracted, Q heat is rejected, in other words. And then we see that the steam is going to get converted into the liquid water, and the liquid water is now subjected to a pump, where from process 3 to 4 we have a pump working in, again compressing the fluid to a very high pressure and pumping back into the boiler. At the boiler again heat is added, basically through the burning of the fuel and in presence of oxygen, and water will be further converted into steam at a very high pressure and temperature. Thereby we see that the cycle continues in a clockwise direction. So steam is going to produce in the boiler at a high pressure temperature, and it will be expanded, the pressure is going to drop and temperature is going to drop, and further we are going to see the partially expanded steam is going to further be converted into liquid state, and it will be supplied to the pump, and the pump is going to pump back the water to the boiler at a high pressure. So we see the cycle keeps continuing. Now this cycle represents a kind of heat engine, where we have heat is being added at one point and then work is extracted at some other point. So we see that there are basically two heat components which are associated with this cycle. We have heat coming in the boiler, and heat is rejected at the condenser. At the same time, we also see there are two work components here. One work is associated with the turbine, which is basically a very high magnitude, and the other work is work input to the pump so that it can operate and compress the fluid. The magnitude of pump work as compared to the turbine will be very less generally. So we see that there are two heat quantities and there are two work quantities, and since it is operating in a cycle, one can apply first law of thermodynamics to this closed system. So we have here cycle integral of heat transfer to the cycle is equal to the cyclic integral of work done. So here we have two heat quantities, therefore we have a net heat supplied, and we have two work components here, therefore we have net work done by the system or cycle. Further expanding these Q net and W net, one can write Q net as heat that is supplied to the cycle and minus heat that is rejected from the cycle is equal to, and work net represents the work that is done by the turbine minus work that is consumed by the pump. So we have turbine as a work producing device and pump as a work absorbing device. So WT minus WP represents net work done. Similarly, Q in minus Q out represents Q net. With this background, one can represent efficiency, thermal efficiency. So we know that efficiency basically is output by input. Here the output is net work done and the input here is the heat supplied. So we have the equation here. Thermal efficiency is represented as work output to the heat supplied, which is given as net work done by heat supplied. So this is the equation representing the thermal efficiency. Now let us move forward. Now since we are having a cycle here which is representing a kind of heat engine, now with the knowledge of basic thermodynamics, we can think of the best reversible cycle which can produce maximum efficiency for an heat engine, and it is obviously a Carnot cycle. Now let us look at a Carnot cycle which can represent a power plant for a steam power plant working process. So here we have a Carnot cycle representing a steam power plant. The various processes which are associated with the Carnot cycle are shown here. We have a saturation dome, which is first part of the saturation dome to the peak represents saturated liquid curve, and the second part of the saturation dome represents saturated vapor curve. So this is for a steam or a water. So we have now process 1 to 2, which is a reversible adiabatic expansion process representing from process 1 to 2. So process 1 to 2, if we just go back to the previous slide, process 1 to 2 represents a turbine work where there is an expansion process that is taking place here. So process 1 to 2 represents reversible adiabatic expansion process where work is extracted from the cycle, and process 2 to 3 represents reversible and isothermal heat rejection. Process from 2 to 3, we see how the heat is rejected out, and this is happening at a constant temperature. Reversible and isothermal heat rejection. It's happening at a low temperature TL, followed by process 3 to 4. We have next process 3 to 4. Again, this process is reversible adiabatic compression process, which is representing a pump work basically. So process from 3 to 4. So this is a reversible adiabatic compression process, and we know that reversible adiabatic represents an isentropic process. Therefore we have point number 3 and 4 on a TS diagram. It is entropy is constant, so S4 is equal to S3 here. So similarly, at this point process 1 to 2, it is a reversible adiabatic expansion process. Therefore reversible adiabatic represents an isentropic expansion process. Since it is isentropic, we have a straight curve on the TS plot. Therefore we have S1 is equal to S2 here. Now moving forward from process 4 to 1, from 4 to 1 represents reversible and isothermal heat addition process. So we have heat being added here from process 4 to 1, and this is happening at a constant temperature condition where we have high temperature TH. So this is about a Carnot cycle representing a steam power cycle on a TS plot. So we see that there are two disadvantages with this Carnot cycle representing the steam power plant. We have state point number 2 and state point number 3. State point number 2 is well within the curve of saturated liquid vapor curve. Therefore it is possessing some dryness fraction, that is called as a quality, which is defined as mass of vapor to that of total mass of the substance or the liquid. So we have a very higher magnitude of the quality here, which is not desirable for a practical applications of a steam power plant. And then when we look at state point number 3, we know that the process from 3 to 4 is a work done by the pump. Therefore the pump is now handling a two-phase mixture region. It is a two-phase mixture which is the pump is handling. Again, this is not a desirable for pump. Pump is designed to handle completely a liquid condition, but here we have a two-phase mixture which is not desirable. Therefore we see that the Carnot cycle, though it is efficient efficiency point of view, it gives us maximum result, but practically we don't see this serving the purpose for steam power plant. Now let us move forward and see what is the best cycle which can fit for vapor power cycle. And for Carnot cycle, again the efficiency of Carnot cycle is given to us as TH minus TL divided by TH, which can be further can be modified and can be represented as shown here, where we have 1 minus TL by TH, where TL represents low temperature of the cycle and TH represents the high temperature of the cycle. Now let us look at next best cycle which can represent vapor power cycle, and that is Rankine cycle. Again, Rankine cycle, we on a TS plot, the curve is shown here. We have a process of expansion in the turbine in two modes. One mode is from process 1 to 2, the other mode is process 1 dash to 2 dash. The difference between the first mode of expansion and the second mode of expansion is very clear. The state point 1 is dry saturated, and state point 2 is well within the saturation dome, so this is possessing some dryness fraction. Now second mode of expansion, we have process 1 dash to 2 dash, and 1 dash is outside the mixture dome, therefore it is superheated, possessing a very high temperature at a pressure of P1. And then we have state point 2 dash, which is much closer to that of the saturated liquid curve, therefore the dryness fraction is much higher as compared to that of state point 2. And this shows one of the advantage of superheating the steam, and thereby one can have a control on the dryness fraction. The dryness fraction, when it comes to the operation of the cycle in practical, the dryness fraction less than 85% is not desirable. It has to be more than 85%. Otherwise the blades of the turbine, which is represented by the process 1 to 2 or 1 dash to 2 dash, it's an expansion. This is happening typically in the turbine. The turbine blades gets eroded because of the presence of moisture, so therefore we want very little moisture as far as possible. Further moving, let us now look at the different processes here for a Rankine cycle. Process 1 to 2 represents reversible adiabatic expansion process, and this is similar to that of Carnot cycle process from 1 to 2. And then we have process 2 to 3. This is represented as reversible and constant pressure heat rejection process. When we compare this with the Carnot process from 2 to 3, that is reversible and isothermal heat rejection, whereas in a Rankine cycle it is heat is rejected at constant pressure condition. So that is a fundamental difference between the Rankine and the Carnot. The process 3 to 4, again we have a pump work here. This is represented as a reversible adiabatic compression process, and this is similar to that of Carnot cycle process. There is no difference. Now coming to the last process, that is from process 4 to 1. This is represented with an ideal process as reversible and constant pressure heat addition. So this is quite different compared to that of Carnot. In case of Carnot cycle we have reversible and isothermal heat addition. So we see that when you compare the Carnot cycle with the Rankine cycle, the heat addition and heat rejection in the cycle is taking place at isothermal condition, at constant temperature condition in case of Carnot cycle. But in case of Rankine cycle, the heat addition and the heat rejection, this is happening at constant pressure condition. So that is a fundamental difference. Now moving further, let us now develop some equations by taking the components one by one. Let us now first take the work components, that is turbine work and the pump work. One can, since the turbine and the pump, they are the open type of systems, one can apply steady flow energy equation and one can represent the work quantities. So we have here turbine work per kg basis, which is given as H1 minus H2. It's enthalpy 1 minus enthalpy 2. So depending upon the pressure and temperature at state point 1 and state point 2, one can refer to the steam table and get the value of enthalpy 1 and enthalpy 2. So this is kilojoule per kg basis, so unit mass basis. Now let us look at the equation for work done by the turbine, by the pump, I'm sorry. So for the pump we have TDS relation. TDS is equal to DH minus VDP. So we can use that, and since this is isentropic process, ds will be subjected to 0, therefore we have dH is equal to V into dP. So using that equation, dH is equal to V into dP, where we have dH as change in enthalpy, that is H4 minus H3 from the TS diagram, and then V represents specific volume, and point number 3 is on a saturated liquid curve, therefore we have Vf at the corresponding pressure. So one can refer to the steam tables to the corresponding pressure and get the value of Vf straightforward. And the dP represents the pressure difference. The pressure, that is boiler pressure, is dictated as a P1, and we have a condenser pressure, and we have a heat rejection that's happening. This is represented by pressure P2. So we have the pressure difference here, P1 minus P2, so we can have dP as P1 minus P2. So we see now one can calculate work done by the pump using these equations, and this is in kilojoule per kg basis. Therefore we have a small w, small letter w, specific heat input by pump. Similarly for turbine also we have small w because it is on per kg basis. Therefore one can call this as a specific work done by turbine. Now moving further, let us look at the heat quantities. Now heat that is added into the system on per kg basis, therefore we have specific heat input which is given as H1 minus H4, straightforward. So these equations we are developing considering steady flow energy equations which are applicable for open type of thermodynamic systems. So we have next heat rejected, and this is given as H2 minus H3, higher enthalpy minus lower enthalpy, and it is on per kg basis, therefore we have specific heat rejected. So these are some of the energy quantities which are associated with the cycle. So taking these equations into consideration, now plugging these into the thermal efficiency equation. So we have thermal efficiency is given as net work done by the heat supplied. Therefore net work done here represents work done by the turbine minus work done by the pump. So we have H1 minus H2, which is the work done by turbine, minus H4 minus H3, this is representing the work done by the pump. Therefore turbine work minus the pump work represents the net work done, divided by the heat input. The heat input is H1 minus H4. So we have the equation here, the final equation for thermal efficiency. Now sometimes the examiner may say that neglect the pump work because the magnitude of work input that is supplied to the pump is very small as compared to the magnitude of work done by the turbine. Therefore one may ask us to drop the term for the work done by the pump. Therefore one can take this H4 minus H3 to 0. In that case we have work done by the turbine divided by the heat supplied. So this becomes the final equations when we neglect the pump work. So these are the important equations when it comes to Rankine cycle representing the steam turbine. Now moving on further, we have now the two cycles in hand. One we have Carnot cycle. We have seen the typical processes that are taking place across the components, and we have Rankine cycle, which is again applied to the cycle, and we have seen different processes. Now let us look at both these cycles being representing the steam power plant. So here we have three figures representing the steam power plant A, B and C. In all these cases we have the Rankine cycle superimposed by the Carnot cycle. So we have TS diagrams here. Now let us look at figure A, where we have process 1 to 2 representing the reversible adiabatic expansion process, and process 2 to 3 representing reversible constant pressure heat rejection for Rankine cycle, whereas for Carnot cycle it is a reversible isothermal heat rejection, and process 3 to 4 are representing reversible adiabatic compression work process, in other words for a pump, and process from 4R to 1 representing reversible constant pressure heat addition for a Rankine cycle. But whereas for the Carnot cycle, from process 3 to 4C representing reversible adiabatic compression work, and from process 4C to 1 representing reversible isothermal heat addition process. So likewise for the rest of the two schematic views or the TS plots, we can see the similar the representation. Now when we compare figure A with that of figure C, we see that process 1 to 2 and 2 to 3, they are quite similar for both the cycles in A and C, for Carnot cycle and as well as the for the Rankine cycle. Therefore we see that the difference between the figure A and figure C comes when it comes to the heat addition process. The heat addition process in case of A and B, when we see the heat addition at the Carnot cycle is much higher, the magnitude. One can see here, if you drop horizontal line to the y-axis and if you drop one more horizontal on the y-axis, we see the heat addition by the Carnot cycle is much higher as compared to the heat addition by the Rankine cycle. Therefore we see that the efficiency of Carnot cycle is higher as compared to the Rankine cycle when we compare figure A and figure C for the same heat rejection, Now let us compare figure A and figure B. We see that in figure A and figure B, the heat addition is similar for Carnot cycle when we compare this. So since it is happening at a isothermal condition from 4 to C and from 2 to 3, when you drop a horizontal line, so the temperatures are same for both the TS plots. Therefore we see that again the Carnot cycle, they have same higher efficiency here, has a magnitude of heat that is transferred is much higher. So we have from figure A and B, we have two Carnot cycles, one from figure A and one from figure B. They have the same thermal efficiency because the heat addition is same. Therefore we see that the efficiency of Carnot cycle is greater than that of Rankine cycle. Now looking at all the three plots, we see that process 3 to 4C in plot number C and in B also, when we see from 3C to 4C and in A from 3 to 4C, the pump work is very high as compared to the Rankine work. Therefore this is very large pump work and it is not practically desirable. So we see that referring to figure A, B and C, pump work is very large for Carnot cycle, so this is not practical. At the same time we see that the heat that is added is at a infinite high pressures, at a very high pressures, and it has to be added at isothermal conditions, which is practically very difficult. Therefore we see that these are some of the bottleneck situations for a Carnot cycle to represent a steam power plant cycle. Therefore when we compare Carnot cycle with that of Rankine cycle fits much better compared to that of Carnot cycle. So here we have efficiency of Carnot cycle, which is typically a function of two temperature limits. Therefore point number 2, when we say refer to point figure A and B, we see that both the Carnot cycles, they have the same temperatures, so they have the same temperatures, their efficiency is same here when you calculate the Carnot cycle. So now let us look at some of the performance equations related to steam power plant. So here we have the first performance parameter, that is thermal efficiency, which is given as net work done to that of heat supplied, and when we multiply this with the 100, then one can represent this efficiency in terms of percentage. Now moving further, we have back work ratio, That means we are going to divide pump work with reference to turbine work. So this gives us back work ratio. Then we have work ratio, where we have net work done by the cycle, which is work done by the turbine minus work done by the pump divided by turbine work. So this gives us a work ratio in kilojoule per kg basis. And since it's a ratio, we don't have a unit here. And next we have the capacity of steam power plant is often actually it is represented in terms of steam ratio, which is defined as the rate of steam flow in kg per hour required to produce unit shaft output of around 1 kilowatt. Therefore one can represent this as 3600 divided by the net work. Therefore we have the units kilojoule per kilowatt hour. We have similarly the cycle efficiency. Sometimes it is alternatively represented in terms of heat rate, so which is defined as ratio of rate of heat input Q1 required to produce unit work output, that is 1 kilowatt. So we have here 3600 divided by the cycle efficiency with the unit kilojoule per kilowatt hour. So these are some of the important performance parameters associated with that of steam power plant. Therefore with this we have now come to the end of today's lecture. Let us recall what we have studied in the today's lecture. We have looked at a schematic view of steam power plant. We tried to identify various subsystems. Among that we picked up a subsystem B, in which we had 4 important components. Those are the turbine, condenser, feed pump, followed by the boiler. And then we looked at one of the best efficient cycle for a heat engine. And since the working of steam power plant representing a kind of heat engine, so when we looked at a Carnot cycle, we saw that practically it is not desirable, and we identified another alternate reversible cycle, that is a Rankine cycle, which has fit very well for the steam power plant. Therefore Rankine cycle is the ideal cycle representing thermal power plant or steam power plant. And then we have looked at different equations across the various components of a steam power plant. We have applied steady flow energy equation, and then we have looked at the heat quantities and work quantities, and we have plugged those quantities into the thermal efficiency equation, and we expressed the equation in terms of enthalpies. And at the end we also looked at performance parameters as shown here. So with this we have come to the end of today's lecture. Thank you for your attention.